Where does mass come from? New discovery reveals an exotic state in the atomic nucleus.
Almost everything around us has mass, but the origin of this mass remains one of the great questions in physics.
Current theory explains that mass arises from the properties of the vacuum, which is not empty space, but a complex and invisible structure that permeates the entire universe. One way to investigate this is to study mesons, particles formed by a quark and an antiquark that can briefly bind to atomic nuclei. These systems, called mesic nuclei, help to understand how mass is generated and how the vacuum behaves in extremely dense environments, such as the interior of an atomic nucleus. Now, an international team of researchers has found evidence of an exotic state long predicted but never observed before, the eta prime mesic nucleus. The results were published in the journal Physical Review Letters. Eta is a heavier meson than other similar mesons. Scientists believe that its mass may change when it is inside dense nuclear matter. Observing this change offers valuable clues about how particles acquire mass in the universe. To conduct the experiment, researchers sent a high-energy proton beam against a carbon target at the GSI Research Center in Germany. This collision excited the carbon nuclei, allowing eta mesons to be produced and possibly become trapped inside the nucleus, forming a bound state.
They measured the excitation energy of the nuclei by analyzing deuterons, particles formed by a proton and a neutron, emitted in the reaction, using high-precision equipment such as the fragment separator, FRS, and the Wassa detector. The data showed structures that correspond to the formation of these eta-bound states in the carbon-11 nucleus. The results indicate that the mass of eta likely decreases when it is inside nuclear matter. This supports theoretical predictions and provides one of the first experimental pieces of evidence of how particle properties can change under conditions of extreme density. As lead researcher Kenta Tahashi explains, these measurements offer new clues about the behavior of mesons in nuclear matter and bring us closer to answers to fundamental questions. How does matter gain mass, and how does the vacuum structure change within atomic nuclei? Future experiments aim to increase the precision of the measurements and search for more decay signals to definitively confirm the existence of these eta mesic nuclei. Each advance helps to unravel the basic laws that shape the universe and explain why things have mass.